Welcome to the second lecture on principles of vibration control. If you remember that in the last lecture we have talked about various vibration control strategies, and particularly we have focused on reduction of excitation at the source itself. In fact, on that category we have talked about vortex induced vibration, and I also said that how you can use the knowledge of Strouhal number, the relationship between Strouhal number and Reynolds number, and with the help of that how you can redesign your system. There are also a few more tricks involved with it, which we will be discussing today. Also along with that I will talk about other vibration control strategies like vibration isolation at the source itself. Then we will talk about considering the vibrating system, how we can redesign the vibrating system, and finally we will talk about some of the remedial measures in it. Then I also intend to tell you, summarizing the whole thing, that in case of a vibration control problem, what are the steps that one has to take one by one. And finally, I will touch on a very important I would say adjoint part of this vibration control, because in the first itself I told you that vibration control itself is nowadays broadly divided into two categories, right. One is passive vibration control, where it is essentially a open loop system, the system response is not needed, and another is active vibration control, where the system response is definitely needed and a closed loop is to be developed. So, that also I will initiate today. So, this is what is our plan for this lecture. Now, let us first talk a little more about the control of the vortex induced vibration, how to control such vibrations. Well, if you have a uniform stream velocity, okay, the stream velocity is essentially the flow angle relative to the structure should remain constant. In such cases you can actually design a streamline Pyre system, which is like of a particular angle, in this case it is 10 degree. So, one can do that from the structure fluid interactions, and one can get an optimal design, but this kind of a shape of a Pyre which is streamlined. So, this is the upstream side and this is the downstream side. So, you can actually by designing this you can get a good vortex you can stop the vortex separation essentially by designing this kind of a Pyre. You will see these next time if you look at it, that in many of the bridges, if you look at it, you will see that this technique is definitely used to cut the source of vortex induced vibration. There is another thing also, you will see that in chimneys or in silos, that you will see that they actually use some kind of a spiral stair all around a chimney or a silo. So, next time if you look at a silo which is used for storage of, let us say, cement and all such things, so you will see that this type of a spiral is built all around it. Now, this spiral not only gives an access in terms of the control of the structure etc., but also it helps immensely in terms of breaking the regular vortex pattern. This is a very common technique that is used for various types of silos and chimneys, and this is also known as the helical spoiler category. In marine, particularly for the offset structures like cables etc., they use a slightly different strategy in this case for vortex separation. Here in this case you will see that they use plastic ribbons which is generally woven with this structure itself, the cable structure itself, and typically they are quite big. For example, if this one is of diameter d, you would see that this is also of the same type of a size, and the separation also you will see of a very much similar level of D, and generally this kind of a cantilever is about 4 times the D. So, this is actually used for underwater cables as spoilers, okay, and this is used for cutting down the vortices, so that the cable does not get affected by the vortices that will generate in a marine kind of an ambience. Now, there is also, I have not mentioned it here, but I remember that for submarines also they use something in the tip of a submarine. You would see invariably that if this is a submarine body, and then they have a periscope which actually they use in terms of watching what is happening over water, and you will see that it also has a kind of a spoiler in it, a kind of a spike which actually works like a spoiler, and that is used in terms of the submarines. So, there are such various types of vortex induced vibration control system that is used in terms of reduction of vibration at the source itself. Next, I will talk about isolation of the vibration. That means, in this case vibration at the source is not controlled. So, if there is a source, the source is giving you excitation. So, excitation is coming and you have to save your system. So, next is the system in line. Now, how to give some kind of a barrier between the two, so that the excitation at the source does not disturb the system, that is what we have to think of in terms of isolation of the source. So, let us see what are the things that we can do for it. Well, as I earlier told you that you can use various types of springs or dampers, okay, springs or dampers or viscoelastic materials which works like partly as a spring and partly as a damper, or pneumatic suspension. So, you can use these type of things. That means, you have to use them as an insertion between the source and the system, so that the vibration from the source does not get transmitted to the system. And many a times this is like a very common anti vibration mount you will find, in which you have rubber. So, this works like a damper, and you also have the metallic inserts here, and this is serving two purposes. One is that it forces the rubber, it enhances the energy dissipation in the rubber, and the other thing is that it also works like a good spring candidate. So, and then there are studs with which you can fix it. So, essentially you can use this type of a system in terms of a combination of springs and dampers, you can say, and for vibration isolation from a noisy source to the system. So, this is like with the help of, we will call it viscoelastic material based isolation, and we will later on talk about more about this kind of material properties. Now, I will bring you to a very good example, which is the example of a woodpecker's head which inspires the shock absorption. Before I actually explain this part to you, let us just see an woodpecker in action. As you can see here, that this is a woodpecker which is hitting on a stem of an old tree. Now, you just see how it is working on this particular tree, and you just note down that it has a very sharp beak. In fact, the beak is very rigid. So, first of all, it is choosing a suitable spot, okay, where possibly it is good for its beak, and you see now it has actually chosen this part, okay, and it is chiseling out the wood bit by bit, okay, and the entire purpose is to build a small hole and a nest inside, so that it can lay eggs, etc. And you see how effectively it is removing the wood in order to make a very nice hole, and which can be used in the form of a nest for the woodpecker. this particular thing of course costs woodpecker a lot, because if you really follow the type of number of times it actually does this, it is a quite an enormous shock, and as well as it is a very fast process, and everything it is doing by endangering its brain. So, the nature must have done something in order to save its brain. So, now that you have seen that the woodpecker has made beautifully this hole, let us go back and see what are the things that this woodpecker has done in order to save itself. So, let us see the strategies that the woodpecker has actually taken in order to save itself, its head, and yet continue with the beautiful way of actually of making holes in a stem, in a solid stem. See, you may find that this beating frequency could be something like 20 to 30 kind of 20 to 30 hertz or so. So, and the deceleration is something like 1200 G, because the beat is the beak is striking the stem and it has to stop, dead stop, transfer the entire force, and once again it has to do the same thing. If it continuously vibrate, then the hole will not be done at a very nice manner. Now, in order to save the woodpecker from the brain damage, the way the nature has designed this system, there are a couple of things which are very interesting. One is that it has given it a beautiful spongy bone structure. The spongy bone structure is such that it can actually absorb the shock of much of this shock. The beak itself of course is very rigid. These beaks are very rigid, and the tongue is connected to a hyoid elastic layer all around in such a manner that the load gets very uniformly distributed all over the skull. Not only that, between the brain and the skull you will always see that there is a small gap that is provided by nature, so that the brain matter does not get disturbed when the woodpecker is going to actually hit the wood at such a tremendous speed. Now, one of these things, this spongy bone, that it indeed works, I just want to show you with the help of a very small experiment. What we have in front of us are actually two glasses. One glass is empty, and in another glass I have filled it up with small glass marbles. Okay? Somewhat like I have tried to make an imitation of the kind of a spongy bone system that an woodpecker will be having. Now, if I hit this one, in which there is this kind of glass beads are absent, you just see what is the sound that it is producing. So, you can see that is a distinct ringing sound is coming from these glass and this sound is continuing because there is no way this energy is dissipating into the system. Now, in the second case you have the glass beads there, and if I hit it with the same intensity, you can hear the third sound, which is not at all ringing like this. So, what it means is that whenever I am striking this, the vibration, the mechanical energy is not able to excite the air inside, rather the energy is getting dissipated because of the frictions between these beads, all these beads, in fact that is dissipating the entire energy. So, that is the strategy that these woodpeckers take in terms of the spongy bone, and so that the vibration gets isolated and the vibration does not travel from that beak side to the brain matter. So, we have seen how these woodpeckers have been able to absorb the shock, work as a beautiful shock absorber, and the entire structure is designed in such a manner that there is a good isolation of vibration that is possible in the system. Now, let us go to another way of vibration control. This time we will talk about system redesign. Let us see how we can do this system redesign for controlling the vibration. I earlier told you that any system, vibrating system, generally would have three parameters: the mass m, so this is a single degree of freedom system, the stiffness k, and which is measured in terms of Newton per meter, and the damping constant. Let us say if it is a viscous damping, then the viscous damping coefficient is Newton second per meter. So, this is the single degree of freedom system which has these three parameters: stiffness, mass and damping. If you really look at the first of all the response of this system when it is subjected to a harmonic force F, let us say F is a harmonic force, something like F bar e raised to the power j omega t. So, that is a harmonic excitation that you are giving to this single degree of freedom system, and if you plot the non-dimensional frequency versus the magnification factor, which is a ratio of amplitude of the system, and what you will find is that up to about 0.4. So, the at the peak frequency the non-dimensional frequency is unity. So, up to about 0.4 you would see that this response of the system, or so to say the magnification factor, is purely controlled by the stiffness factor. We have to keep this point in our mind. Later on I will derive this thing to you, but right now let us keep this point in our mind. So, that means until and unless the excitation frequency omega reaches a level where it is more than 40% of the natural frequency, the vibration can be controlled by stiffness itself. So, if I have to modify the system property, I would not touch the mass, I will not touch the viscous damping coefficient, I will only modify the stiffness of the system. Beyond that, from 0.4 to somewhere very close to unity, generally up to the half power point, it is controlled by both stiffness and mass in both the sides. And between the half power points, okay, this region, it is actually the resonating region where it is damping controlled. So, the resonating region between the two half power points more or less is actually damping controlled. And once again, beyond the value of about 3 or so, greater than 3, this region onwards the response is actually mass controlled. So, that is also interesting. If it is a very high frequency excitation beyond the peak frequency, in that case neither stiffness nor damping would actually help us in terms of controlling the vibration, but only the mass of the system will help us in terms of controlling the vibration. So, whenever we will go for system modification, we have to keep this point in mind, that at what part of the frequency excitation we are talking about. If it is small, then it is stiffness; if it is close to resonance, then it is damping; if it is beyond a certain point, then it is mass, and in between we have positions where it is both mass and stiffness control. Now, to do that, to implement that, there are certain strategies that one can do, like detuning, decoupling, or placement of additive damping treatment, which can be constrained or unconstrained, then stiffeners and massive blocks such as foundations or water tanks, etc. So, these are all various strategies of system modification, but the basic fact we have to keep in our mind. Now, let us see that how we can do this in terms of structural materials or in terms of viscoelastic polymers. So, structural materials like metals and alloys, stiffness of course you can change, and how you can do it? If you change the modulus of elasticity or the shear modulus or the bulk modulus. So, these are the three things, right. So, this is the elastic modulus or Young's modulus, and then G is our shear modulus, and then K is our bulk modulus. So, by actually changing E, G or K, you can get a change in terms of the stiffness for the metals. You can also change the damping and the loss factor by choosing a suitable material, and for metals, once you choose this material, it generally remains constant. That means, it is not a function of the most important thing, the temperature, because the temperature is one parameter that affects a lot, particularly the polymers and the viscoelastic materials. The other thing is, of course, in a high frequency regions etc., wherever mass controls the response, then you can actually control the density and the geometry of the system. So, to give you some kind of an idea, like aluminum, it has the lowest density in terms of the damping material that is used, but its loss factor is also very low. If you consider brass, it has a higher density and its loss factor is also very low. No wonder that is why brass is used in terms of musical strings, where it does not have a high loss factor, that is why it is used. And in terms of modulus of elasticity, aluminum's modulus of elasticity is 72.5 gigapascal, whereas brass is about 104. So, it is slightly stiffer than aluminum. If I go to steel, then the density will be higher than aluminum, about 7800 kg per meter cube. Modulus of elasticity is about 3 times high. So, that means you will gain in terms of the stiffness, and also you will gain in terms of the loss factor, because this is of the order of 10 raised to the power minus 3. So, which means in comparison to aluminum, you will get 100 times more energy dissipation if you consider steel. If you can go for cast iron, you will get a little bit of weight advantage, it is about 7300 kg per meter cube. Modulus of elasticity will come down, which means the K, the stiffness will come down, but the loss factor is 10 times better than steel, it is about 10 raised to the power minus 2. If you go for copper manganese, a 40:60 ratio of an alloy, you get nearly the same kind of a thing, but the better part from cast iron is that cast iron is more breakable, but this is better, more ductile etc. If you can use concrete, then your density is about the same level as aluminum, modulus of elasticity is not very high, and the loss factor you will get of the same level as cast iron or copper manganese alloy. So, we can see that metals up to a certain extent, it can be used in terms of a damping material, and also in terms of, particularly in terms of giving a high stiffness, because most of the metals have high modulus of elasticity. In fact, one of the metals that is used today is an alloy of iron chromium. It is called FeCr alloy, okay, which is having a much better loss factor. Now, in comparison to this, if you want to enhance the loss factor further, you have to go to viscoelastic material. But the only problem with viscoelastic material is that their property would not remain fixed, they are frequency and temperature dependent due to their change in configuration from glassy to the rubbery phase. So, if you want to gain in terms of the loss factor, stiffness of course you would not gain much, because modulus of elasticity is not very high, but if you want to gain in terms of the loss factor, you have to lose in terms of this temperature dependence and frequency dependence of the property. If I look at it, that how it changes, you would see that if temperature remains constant, which is theta equals to constant, in the top two cases, there are two modulus that is written here, one is the shear modulus, the real modulus also, and the other one is the loss modulus. So, the elastic modulus G, I later on explain the details of it, is divided into two parts, G prime plus G double prime. Okay. So, G prime will approximately vary in this manner, whereas G double prime, which is the loss modulus, will vary in this manner. So, what you will see is that when the frequency of excitation is low, in that case the shear modulus is low, and as the frequency of excitation is increasing, at a particular point there is a sharp jump that would be initiated, and then at a high frequency the shear modulus will be quite high. Now, that is particularly the real part of the shear modulus. Why is it so? So, it means that these polymers actually are pretty dumb if the excitation frequency goes beyond a particular range, which is known as omega critical, or the critical frequency for the particular polymeric material. In fact, it will have, since it will not be able to dissipate energy much beyond that level. So, what you will see is that around this region of omega critical, you will see that the loss modulus, that is G double prime, would increase sharply. But before this and after this, that means if the excitation frequency is much lower than omega critical or much higher than omega critical, then at a constant temperature you would see that the loss modulus is not very high. So, what it means is that at the glass transition temperature, which actually is the same in terms of the kind of a mobilization of the chains of the polymeric material that happens at close to that particular frequency, but around that frequency level, okay, and the glass transition temperature and this critical frequency are actually having an equivalence between the two, but around that level this chain mobilization occurs. So, the loss factor increases enormously, but before and after it will not be very high. Now, if you change the temperature, you would see a very similar picture, in the sense that increase of temperature is equivalent to decrease of omega. So, as the omega decreases and the temperature increases, you will get a similar picture. That means, at low temperature you would see that it has a high shear modulus, but as the temperature increases the shear modulus becomes quite low, which means the stiffness is changing. In terms of the loss factor of the damping, at low temperature once again the damping is not very high, but beyond a particular temperature the glass transition happens, this region once again, and the chain mobilization occurs. So, you get a good loss factor here, and after that temperature once again that loss factor drops down. So, this property we have to keep in our mind in terms of modifying the system parameter. Finally, I will come to the case of vibration control strategy in terms of the remedial measures. So, let us see some of the examples of it. Now, when we are talking about remedial measure, we are actually telling that in terms of isolators you have already tried and is not giving a good result. System modification in terms of change of mass, change of stiffness, change of damping, you have tried it, but it is not giving good results. Then the thing that you can try is to add a secondary vibrating system to the original vibratory system, which is under excitation. Such secondary vibration systems are sometimes called vibration neutralizer, vibration absorber, tuned, self tuned, impact absorbers. There are many names of it. If you remember, I have shown in this course, in the introduction of this course, a stock bridge damper, which is a kind of a secondary vibrating system. But this strategy has been very successfully used for electric hair clippers, DC-9 aircraft, tractors, footbridges, pipelines, etc. So, that is about the use of the remedial measures of a system. Next, if you think of other viscoelastic materials that can be used for system modification, you can go for additive damping treatments like constrained and unconstrained layers. So, you can have a viscoelastic layer which is just above a plate as a free layer, we call it as a free layer damping. So, this is also known as free layer damping, or FLD. As you can see that here the loss is taking place mostly because during the extensional deformation in the viscoelastic material the energy loss takes place. On the other hand, if you put a constraining layer on top of the viscoelastic material, then there will be unequal shear between the two layers, and that will create a lot of shear in the viscoelastic material, and that is known as the CLD or the constrained layer damping. That is the constrained layer damping. One can actually show that in most of the cases constrained layer damping works better than the free layer damping. To sometimes make it even better, you can actually keep it farther away from the neutral axis by giving a spacer. So, this is one of the strategy that is taken such that this effect gets even further magnified, but this is what we do in terms of adding a layer, but you may also think of it as a system modification. So, what are the steps in vibration control? The first step is identification and characterization of the source of vibration. We have to keep this point in our mind. Then you have to specify the level to which this vibration should be reduced. See, we may say that okay, you bring down the vibration to 0, but that makes no sense. All engineering design talks about some kind of a quantification. So, that level based on what system we are talking about is to be first of all defined. Then at step C, we will talk about the method which will be appropriate for realizing the vibration reduction level, which is identified in step B. And then we have to prepare an analytical design based on the method which is chosen in step C. And finally, we have to realize this in practice. Okay? So, that is what is the last step in terms of the vibration control. So, this is the overall steps that we have to take in terms of the vibration control.